CCE, as this school is known, is promoted by the graduate program of Astronomy and Astrophysics here in the National Observatory and organized by the Department of Astronomy. Right? And the CCE is now 24 years old, right? And I believe that over the last 24 years we have been very successful in bringing very important names of the international community to lecture here. And this year is not going to be different. So it's my pleasure to thank the lecturers of this year's edition, Dr. Dennis Moura, Dr. Joseph Masiero, Dr. Martin Cruz, and Dr. Steve Kramer. Thank you very much for having accepted our invitation, for your effort to come, help you enjoy the school, and I also hope that all participants enjoy this school. So Professor João, who is the director of the National Observatory, is going to say a few words.
Hi, I would like just to welcome everybody, and mainly the speakers for coming. As you know, we are in a crisis in Brazil, a science crisis, and it's very important to keep up with our programs and to show that we continue to do our best to not just for Observatorio Nacional, but also for the science in Brazil. Then I would like to thank the organizers and all the speakers, and I hope it's a very successful school courses here. Thank you.
So everyone can hear me? Yes. Well, okay. Thank you, Julio, and thank you to all the organizing committee for inviting me here. It really is an honor to be able to come down here and get to speak to you all and tell you some of what I know about the solar system. I'm told that some of you are solar system, many of you are not, and so I'm going to start with an overview of what we mean when we talk about the small bodies of the solar system, what we know about them, how we know it, and then how we can use dynamics to study the evolution of the solar system via the small bodies. And my closing lecture will be on NEOWISE mission that I'm the deputy PI of, and as well as the NEOCAM mission, which is our next generation spacecraft that we are proposing, and that was recently announced by NASA as going forward. So I'm going to start today with a little bit of an overview of the small bodies, but I want to give an overview of myself, since I didn't know Julia was about to do all of that. So I'm originally from the East Coast of the US, from New Jersey, just outside New York City. I was born and raised there, and then I went over to Pennsylvania for college, for my undergraduate work, Hawaii for my graduate work, where I was fortunate enough to use a number of the telescopes on Mauna Kea. And so it really is a fabulous site for astronomy. The facilities up there are amazing, and it is heartbreaking to see the pain that's going on right now with TMD. I understand both sides, and it's really a difficult question right now about what to do about the Mauna. And so I hope that we progress forward in a good fashion. But I don't know what the solution is going to be, but that needs to be decided by the people on the Big Island. Now, about 10 years ago, I moved over to Los Angeles, where I got a postdoc at the Jet Propulsion Laboratory. And after my postdoc there, I transitioned to a staff scientist. And I've been there ever since. So I've been there for over 10 years. I showed up 2 months before the NEOWISE mission launched. So we were in the run-up to launch. We got out to the launch facility. The spacecraft went off, and then the data started flowing in. And so I was able to build my postdoc on this new source of data and what we were able to do with it for solar system objects. So, the solar system. When we talk about the solar system, we typically think of the sun and the planets around it. But as interesting as the planets are, I find especially fascinating the small bodies here. Many of the asteroid belt, the Kuiper belt, the comets, the small things in between the planets, because it's these small objects that really tell us what was going on during planet formation. These are the leftovers. These are the things that were discarded, that were not incorporated into planets. And because of that, we can trace various stages of formation via these small bodies. The analogy I like to use is if you went to a construction site and someone was building a house, if you look in the ground, you can find nails and pieces of insulation and broken tiles, cut-offs, end cuts of wood, and you can see what's inside of that house without having to rip the house apart. And it's the same way by looking at these small bodies, looking at what's inside of them, looking at the story they tell, we can figure out how the Earth was assembled without having to rip the Earth open. because no grant would ever cover that. So what we want to do now is study these small bodies, look at what they're made of, and how we can trace this history to get a better handle of why is the Earth here, why is it covered in water, where did the volatiles come from, how does this trace the history of from a cloud of gas and dust collapsing into a star, turning into the Earth and giving us the world we live on today. So if we start all the way back at the beginning, we come from the protoplanetary disk. So originally the solar system was a cloud of gas and dust, and as that started collapsing, you have the nascent star being born, or proto-sun. And some of the gas material gets blown off by the radiation pressure from the sun, but much of the gas and the dust falls into a disk. That which doesn't go into the sun becomes a disk around. And so we have these great pictures from Hubble of these forming star systems. So little baby stars shrouded by their clouds of gas and dust, collapsing into these disks, starting the process of forming planets. And so it's how that gas interacted, how that dust interacted, how these things stuck together that slowly built up from micron-sized grains to 1,000-kilometer-sized protoplanets. And we see pictures of this. So this is from ALMA. This is HL Tau. Again, a gas and dust, a dust disk around a young star. And we can already start to see here the gaps caused, presumably, by planets.
Are these rings real, or are they some interferometric reconstruction artifact?
Well, we'll hear about interferometry later today, but my understanding is that these rings are actually real, that these are observed rings. They are not interferometric problems, that this is, and we've seen this in a couple of systems now so far. I don't know the exact count that Alma's seen, but these rings are real. Now, the rings it's not a direct analog for our solar system, because I believe that this ring here is kind of at the orbit of Neptune, would be for our star. So these are much, much further out than what we would expect. We can't just say, okay, this is Mercury, that's Venus, and that's Earth. This is on a much bigger scale, and so something else is going on. But there are finer, probably smaller rings going on in the center there. And so as we develop better interferometry technology, we hopefully will be able to uncover some of these really fine-grained, really close-in features that might be the birth of terrestrial planets. But right now what we're seeing is the birth of, presumably, gas giants, planets like Jupiter, planets like Neptune. Our basic understanding is that you have these cores of giant planets. This dust and ice and gas, and mostly dust and ice, condenses to something around 10 Earth masses. And once you hit that 10 Earth mass critical limit, you start to be able to hold your hydrogen atmosphere. And so the remaining gas in this disk starts getting sucked to the planet and quickly builds up something the size of Jupiter or Saturn. In the terrestrial region, we see collisions. The gas has been blown away by solar radiation pressure. There is very little gas, and the planets are smaller. A lot of the dust has been swept out as well. And so instead of getting these gas giants, you start building from dust. Dust sticks together as it runs into each other at these slow speeds and builds up to dust bunnies and pebbles, which is probably not the right term, but is about around that size. Pebbles build to asteroids via a method we won't talk about because we don't really know. And then asteroids, once you get up to the 10, 100-kilometer range, things start crashing into each other and joining to form planets. And so this is just an artist illustration of presumably the Mars-sized body that hit the proto-Earth and generated our moon. And so that was one of the very last major impacts of planet formation in our solar system. Now I kind of skipped this pebble to asteroid thing because we have something called the meter barrier problem. And that's if you take objects that are on the scale of a meter and you run them into each other, they don't stick like dust does, and they're not big enough to be totally subsumed and collected by these collisions. They bounce off each other. And so how you get these meter objects to collapse down into something the size of an asteroid is a problem. The current best explanation is eddies in a vortex within the disk cause this slow collapse. So quickly, these materials bond together, and you get these, it's the asteroids are born big idea, that you have these meter objects that suddenly collect into 100-kilometer scale asteroids. And this seems to be traced by the size-frequency distribution we see in the inner solar system, in the main belt in particular. And I'll talk a little bit more about how we get that size-frequency distribution tomorrow. But this is the general picture of how we are forming our terrestrial planets. Now, out past the ice line, things are different. Ice is stickier, and so it seems, as far as we understand, that objects can build more quickly. You have more material, because the ice acts as a kind of dust, so you have a significantly more amount of stuff to stick together, and it's stickier, and so you build planets quicker. And so this was our general understanding of planet formation. Once you get past the line where ice can stay a solid, you build planets quickly, and so you get these big gas giants, you get smaller ice giants as you get farther away. Terrestrial planets are smaller because there's less material, and this was all great until they found the hot Jupiter planets and totally upended our view of the solar system. So now we have no idea how any of that works, and we kind of assume, we hope that this is still the same system and that something different happened to the hot Jupiters, that they migrated to where they are. Otherwise, we have to completely revamp our understanding of the solar system, and in particular, our understanding that's supported by a lot of these analyses I'm going to talk about. So this migration will feature in a little bit. But one other key point in the formation of the solar system was the injection of aluminum-26. Sometime not long after our dust disk formed around the sun, after our sun was born, but before the planets were born, a nearby supernova went off and injected a large quantity of aluminum-26 into our solar system. What's very special about aluminum-26 is that it has a relatively short half-life in the tens of thousands of years. So it was around long enough to be incorporated as these planetesimals were being built. And it produced a lot of heat. And so a large fraction of the internal heat in these protoplanets was from this radioactive decay. And the reason we can trace aluminum is that it bonds very well with the silicates. And so we can see evidence of silicate material in our meteorites, things that had aluminum bonded to it, and the aluminum is no longer there because when it radioactively decayed, it changed and is no longer where it should be. But you're looking at a silicate matrix that's supposed to have aluminum here, and it's gone. And so we have strong evidence for aluminum-26 presence causing a large amount of heat. And what that heat did is it allowed some of the inner planets, like the Earth, like Vesta, to differentiate. It put a large amount, a unique source of heat that allowed all of the silicates to melt. It allowed the iron to flow to the core. It allowed the silicates and the lithophilic materials to float to the surface. This is why we have very little iridium on the surface of the Earth. Almost all the iridium on the surface of the Earth comes from external sources, from meteorites. This is one of the lines of evidence that an asteroid killed the dinosaurs, is a layer of iridium, and iridium excess in that KT boundary layer. So this was a major epoch in solar system formation. And it allowed us to go from these rough accumulation of bodies to things that are like planets. Not everything was big enough to fully melt. And so because we know the aluminum-26 was there, we can start to say, as you look at an object, as you look at something, whether or not it melted tells you how big that object was when it formed. Did it form the size of Vesta? If so, it probably had a melt. If it formed a little bit smaller than that, in the 100-kilometer diameter range, there was not enough heat to melt the body before it radiated to space. And so these things stay more pristine. The larger things melt and differentiate. And one of the signs of this differentiation are the iron meteorites. We have samples of nearly pure nickel-iron material that came from the center of a protoplanet that fully melted, cooled, was shattered, and those pieces are sent to Earth. And one of the problems we have right now is that if you look at the solar system as it exists today, you look at the small body populations, we know of one asteroid that conclusively had melt. That's Vesta. All of the other stuff was swept out. There's very little left. None of the other melted bodies, if there were any, are left. The meteorite record, if you look at the chemical composition of iron meteorites, tells us there are over 100 parent bodies. 100 different Vesta-sized bodies that were originally in the solar system, pieces of which are around today in the meteorite population. I'll talk about later the Arkovsky effect, but what this does is this is a way of clearing small objects out from the inner solar system. And so this poses a conundrum. If we can get rid of stuff in the inner solar system on the billion-year timescale, how do we still have evidence of the cores of hundreds of objects floating around in the solar system if those objects are no longer there? And so this is one of the really fascinating things, is the differentiation in the inner solar system. This also happened in the outer solar system. Ceres is partially differentiated because it's icy. It was icy when it originally formed. A lot of the Galilean moons have very unusual differentiation signatures, where you have varying layers of ice and water, subsurface salty oceans, again, oftentimes from this heating. Some of it's from tidal heating in terms of the Galilean satellites, but a lot of the bigger stuff also had aluminum-26 heating. And one of the nice parts about solar system studies is you actually get hand samples of these protoplanets. We have the meteorites. And by looking at the meteorites, by looking at what this fine-grained structure of each individual meteorite is, you can go back and you can trace the history of these bodies. And so you can see these calcium aluminum-rich inclusions, these white things. These are high-temperature minerals. They were the first solids to form in the solar system. When the dust disk was thousands of degrees and cooling off rapidly, these things were the first to condense out. And we know that partly because they're high-temperature minerals and that's how things should work, but also you can see sometimes CAIs embedded inside of chondrules, which are also high-temperature glassy substances, but slightly cooler. They form at cooler temperatures than the CAIs. And these chondrules here, so this is a nice one, but all of these little round pebbles, in some cases make up 90%, 95% of the material in our meteorites. And how you form these chondrules is a current subject of study. We are not sure how you get these chondrules formed, because they had to form in such a way. We know by the minerals inside the chondrules that they cooled rapidly, but not instantaneously. They're like glassy beads. They're almost glassy beads, but they cooled a little bit slower than that. And so you can easily make glass beads, glass spheres, by crashing two things into each other, and they spit out large amounts of liquid silicates that form into spheres. They cool, they make glass, everything's good. Except if you do that in the present space today, they would cool so quickly that we would not see the mineral structure we see in chondrules. So these had to cool at hundreds of degrees per hour, not hundreds of degrees per second. It had to be a unique period in the solar system when there was still hot gas and dust around, but not too much, not opaque. It couldn't have warmed them up too long. And so the chondrules set an interesting boundary on when the solar system was forming and when they formed. And the fact that they are so frequently present, that so much of our meteorite collection is full of chondrules, says that whatever the process was had to be common. There had to be a lot of it going on. These epic collisions between 1,000-kilometer planetesimals didn't happen very often. But some process was making large quantities of chondrules all over the inner solar system. And so this is another topic of study. How do you get chondrules? How did they form? Ongoing numerical simulations trying to say, okay, was it lightning in the disk? Was it localized heating? Was it, again, these toroidal things going on in the disk, sorry, I'm forgetting the word. But basically, the disk is having, eddies in the disk forming chondrules, heating it up locally just enough. This is a subject of study. We're not really sure. But they are incredibly fascinating looking at the chondrules. So when I talk about small bodies, there are a number of different populations that fall under the heading of small bodies, and they're mostly distinguished by how big they are and what their orbits are. And so we have the asteroids and the comets, which are roughly larger than, say, 10 meters or so, up to 1,000 kilometers in size. The difference here mostly being phenomenological. Do you see a tail? If so, it's a comet. If you don't see a tail, it's probably an asteroid. We have Kuiper belt objects and trans-Neptunian objects, these things that formed out at Neptune or beyond Neptune. They're mostly ice, but they're in a regime where solid water ice acts like rock, has the same structural behaviors. And as we saw with the Pluto flyby, nitrogen acts as a semi-liquid, semi-solid out there. And so they're in a very interesting dynamical regime. We also have the Oort cloud. So these are objects at the very edge of the solar system, a third of the way to the next star. objects that formed here, but were pushed out to the very edges. When we get to smaller objects, we look at meteoroids and dust. These are also considered the small bodies of the solar system, how the dust moves around our solar system. We have dust counters on a number of the spacecraft that we send up. There's missions proposed constantly to look for new quantities of dust, because where this dust comes from is short-lived. The solar radiation pressure can blow dust away very quickly. And so how the dust interacts with the sun and how it forms and how it leaves the solar system can tell us about the processes going on. And then most recently, we have interstellar objects, whereas a couple years ago, they had been conceived of but never seen. And in 2017, we got our first one, Oumuamua, which was so outside the realms of anything we thought we would ever see, it was incredibly confusing. Luckily, a few weeks ago, we got interstellar object 2, Borisov, discovered by, oddly enough, an amateur astronomer in the Ukraine, working with a 60-centimeter telescope. And the reason he was able to find it is he was looking about 40 degrees from the sun, where all the surveys don't look. And so, luckily, Borisov is exactly what we expected interstellar objects, and we can kind of forget about Oumuamua for the moment, the same way we forget about the pulsar planets, because they're very inconvenient for all of our models. But we have these objects. We're starting to see small bodies from other stars passing through our solar system. And the similarities and the differences between the interstellar objects and our small bodies will help us say how common is our solar system. The formation events that happened here, are they unusual? Are they regular? And this is why these interstellar objects are so fascinating. And so as the next generation surveys come on, like LSST, we expect to see order of magnitude or more improvements in the numbers of objects we detect. We can start studying them as a population. There's already people talking about how would we send a spacecraft to fly by one. These things come in at v-infinities of 30 kilometers a second. They pass by the sun at 40 or 50. Oumuamua, I think, had a 90 kilometer a second swing by the sun at perihelion. So there's no way we could ever orbit this in the near future. But a flyby mission, a rapid flyby, but any flyby, would be incredibly interesting. And so this is kind of the next horizon in small body science, is this new class of objects that we only found out about in 2017. So I said size helps us differentiate small bodies, so do orbits. And so just in case you haven't done orbits in a while, this is what the solar system looks like. As we know, the planets are mostly in a plane, and this is because that dust disk, when you have a disk around anything, it tends to collapse due to mutual interactions into a fairly flat disk. If we look at the rings of Saturn, same effect. We have a very thin disk of ring around Saturn because the interactions, anytime dust bumps into each other, it tends to lose inclination. And so our solar system, the planets of the solar system, are generally in a flat plane. And any deviation from that flat plane is one of the ways of encoding this history of evolution. But the small bodies tend not to be. So in this, I'm just showing here, so for example, this is Earth. This is a random asteroid, where I believe that random asteroid is Ceres. And so asteroids have typically more eccentric orbits than planets. They typically have higher inclinations. Now, if we want to say where any given small body is, or any given object in the solar system, you can do that with 6 numbers. You can do that by an XYZ vector from the sun, and a velocity vector, an XYZ, and now you have uniquely stated the position and orbit of a body. Because all the motion in the solar system is Keplerian, and on my talk on Thursday, that's not totally true, but their orbits evolve. But for now, we can assume that these orbits are basically Keplerian around the sun. And so with 6 numbers, and obviously a time, a date that those numbers are valid on, you can uniquely state the position and orbit of any body. But these are very inconvenient, because x, y, z, vx, vy, vz are all changing constantly. So in the study of small bodies, we tend to use a different set of numbers. And you can do pretty much any different set of 6 numbers plus a time can be converted, if you pick them right, into these velocity vectors. And so what we look at instead is the semi-major axis of the ellipse of the orbit. So effectively, how big is the long axis of the orbit? The eccentricity of that orbit, how the inclination of the orbit with respect to the plane of the solar system, or more typically with respect to the plane of the Earth's orbit, because since we're on Earth, it's convenient to measure things against our orbit. So these are the three of the numbers we need: semi-major axis, eccentricity, and inclination. We need 3 other numbers, and those are where the object rises above the plane of the solar system, that angle with respect to some 0 point, in this case the first point of Aries. How far from this ascending node is the perihelion, and then where along the ellipse on a 360-degree scale is the object. And with those 6 numbers, plus our time, we can, again, uniquely state the position of our asteroid. So the reason we like this is because semi-major axis, the average distance from the sun of a body, is a useful discriminant for what population the object is in, whether or not it's stable. And so here I'm showing, so this is log of semi-major axis in AU. So AU is the one Earth-Sun distance is an astronomical unit. And the number of objects in our current catalog, so it's just downloaded every small body known, all 790,000 currently in the Minor Planet Center's catalog, and just plot up a histogram of their semi-major axes. And what you can see is that it's not flat. There are these regions of stability. This red line here, this is a rough order of magnitude debiasing. So this is just a 1 over r squared relation. That would be what you would expect, given that light to detect objects we're seeing in reflected light. So you have a 1 over r squared fall off in light as it gets to the object from the sun, and you have a 1 over r squared as it comes back to the Earth, and then you have a diameter squared of the object. So you expect a -2 power slope. And so this is very roughly showing our sensitivity limits. Basically a flat sensitivity. And so what you can immediately see is that the main belt here, so this is the objects between Mars and Jupiter, are very populated. The Trojan objects here, those in 1-to-1 resonance with Jupiter, are still a large population, but not quite as big as the main belt. And that out here, the Kuiper belt, already is significantly larger than the main belt. So the number of objects out past Neptune dwarfs the number of objects between Mars and Jupiter. It's just that the asteroid belt is significantly closer, so it's easier to detect. But all of this region here, there's almost nothing there. This is unstable. Out past here, it's likely that nothing formed out there. So anything that's out here was scattered by the planets of our solar system. And so there are a few surveys that are conducted that are finding these objects. And so what this is this is someone who said, I'm going to do a very good survey in that direction, do a super deep survey and find all the small things. So take a lot of time on a big telescope and find as many Kuiper belt objects as I can to answer the question of what's that distance distribution. But it was incredibly expensive in terms of telescope time, so they haven't done that for the whole sky. As LSST turns on, LSST is going to be phenomenal at finding Kuiper belt objects. As that turns on and that data stream starts pouring in, after about it takes 3 or 4 years to discover a Kuiper belt object. They move very slowly, and so you have to have multiple passes around the sun by the Earth to see enough motion to lock down an orbit. So about 3 or 4 years after LSST turns on, expect to see this kind of density throughout the entire Kuiper belt. Caveat, the galactic center, where it's very difficult to find stuff. So if we zoom in now, so again, this is the ring of Jupiter, so let's look right in there at the small bodies that we know. Let's look at the inner solar system. So this is what the inner solar system looks like. Here's the Earth. All of the green objects here are the main belt asteroids, that region of stability between Mars and Jupiter. Blue objects are the Trojans. These are locked in a 1-to-1 resonance. So Jupiter is right down here. 60 degrees ahead and 60 degrees behind is the Lagrange 4 and 5 stability points. And so these objects are trapped in this long period libration. Now, this is of course instantly a problem if this is a gravitational well that you can't get out of. You can't get into it either. And so how you populate this region, what sort of dynamics you invoke to get stuff into there so it can be trapped to today, again, sets constraints on what the motions of the planets could have been early on in our solar system's history. All the red objects here are the near-Earth objects. These are the ones that pass close to the Earth and that are potentially hazardous. And so my talk on Friday is about the NEOWISE mission and our upcoming NEOCAM mission. And our goal for that mission is just to find those. Is to find 90%, over 90% of the 140-meter or larger asteroids that come close to the Earth. And again, the main belt looks more populous than the Kuiper belt did in the last slide. Just because it's closer, it's easier to detect, and the way the size distributions work, as you go down a decade in diameter, you go up around 2.5 to 3 decades in number of objects. So a little bit of extra sensitivity gets you a whole lot more in terms of number statistics. So there are about, again, 700,000 objects on that.
Those news correspond to stability orbit, or they're coastline migration?
No, so near-Earth objects are only stable for around 10 million years on average, some much less, some a little bit more, but the median survival time of a near-Earth object in space is around 10 million years. Part of that is because they pass by terrestrial planets. They hit the Earth, they get scattered by the Earth, they run into the sun, they get kicked out of the solar system by Jupiter. That's the end fate of most of these near-Earth objects, but they are not stable. They can only have been put in here in the relatively recent past. And so, if you bring back samples from a near-Earth object, like Hayabusa 2 and OSIRIS-REx are going to do, you are looking at samples from objects that were only recently in the near-Earth population. 10 million years ago, they were main belt asteroids. And so tracing that history, these let you see small objects that you can't detect in the main belt, for example. So the solar system, our plot of the solar system didn't always look like this. If we go back to 1800, 200 years ago or so, this is what the solar system looked like, the inner solar system. So you have Jupiter, you have the terrestrial planets, that's all we knew about. Everything was good. About 4 years before, Uranus had been discovered. And people said, aha, there were more planets out there to find. And this gap here had always been a problem. People have been trying to fill this gap with a missing planet or something. It was just inconvenient in terms of the worldview of astronomy at the time. So surveys began to find the missing asteroids. And very shortly after the discovery of Uranus, we found Ceres, and we said, done. We found the missing planet. And then time went on, and 20 years later, we found 4 more. And we said, okay, there's 5 planets in there. Inconvenient, but all right, that's good. And then there was a gap of time, and then the surveys continued to find more and more objects. And we went from having 8 planets in the solar system to 10 to 30. Eventually said, oh, okay, this is a band of bodies. This is a belt. We will demote all of these objects from their planethood to asteroids, star-like objects. And so that was all good for a while, and that's a very similar story if you read about Pluto. It's just that Pluto had better PR department than the asteroids ever did, and so everyone still thinks Pluto's a planet. It's not, it's one in the belt. But that took us to today, and you saw a couple ramp-ups in the number of objects here, and the way they're plotted. In the 70s, a few dedicated surveys were done to try and look for Trojans, to try and look for main belt asteroids. In the 90s, in the mid-90s, a whole bunch of surveys went online specifically to find asteroids, and that's when the true ramp-up happened. Does anyone know what happened in the mid-90s that would have caused a major investment, especially in the US, in NEO searches and asteroid searches? Anyone want to guess? 96.
The discovery of the gate boundaries, they concluded that
Yeah.
could be a threat.
Yep.
Futures.
So the mid-90s, the KT boundary was, the KT impact crater was found, the Chicxulub crater. Anything else? Shoemaker-Levy 9 hit Jupiter, right? Major comet crashes. People had said, okay, maybe stuff hits us, but how bad could it be? And then a couple kilometer hunk of rock made a hole in Jupiter the size of the Earth, and people said, oh, it can be bad. But the biggest thing that happened for asteroid surveys in the mid-90s was the movie Armageddon. I kid you not. And Deep Impact, but no one ever remembers that one because it didn't have Bruce Willis and it didn't have that really popular song. But seriously, the Armageddon brought it into the public eye. And all of a sudden, asteroids went from bean counting to saving the world with Bruce Willis drilling into an asteroid. And so funding appeared because of it. So never underestimate the power of movies is the moral of that story, which is why JPL's in Hollywood, I guess. We did win Emmys recently for the Saturn descent. That was fun. But this is the top-down view of the solar system. But this hides one aspect of the solar system. And so if we tilt the solar system over on its side, what we see is that, again, the asteroids are not in a nice plane. They are in a puffy cloud around our star. And again, it's that puffiness, it's that inclination of the orbital distribution that tells us how these things formed and what could and could not have been happening to them over the last 4.5 billion years. And so so this is an interesting plot, but not very useful scientifically. So I prefer to unwrap the asteroid belt. And so instead of looking at it this way, I want to fold all the objects and take their average distance from the sun and the inclination of their orbits. And so by unwrapping this and plotting this up, you can start to see structure in this distribution. And so this is the main belt of asteroids. Now, again, I've plotted everything on here, but there's so few NEOs, and the Trojans and Hildas are out here or so. But there's so few objects that the main belt dominates any of these plots by number you do. And again, this is just average distance from the sun and orbital tilt. And so what we're looking at is something like this. Now, you can already start to see, even within the belt, the distribution is not uniform. You have clumps of objects here. These are the asteroid families. I'll be talking about them on Thursday, about what they tell us about the history of the asteroids and what we can learn from the distribution of these families. You also see gaps. These are the mean motion resonances with Jupiter. Jupiter is the big bully of the solar system. If you're in a 2-to-1 or 3-to-1 or 5-to-2 resonance with Jupiter's orbit, you're gone. The gravitational interactions very quickly excite your eccentricity, throw you up, and then you either hit Jupiter or you hit the sun or you're ejected from the solar system in the span of tens of thousands, hundreds of thousands of years. Astronomically speaking, very short. So these are cleared out by the gravity of Jupiter. This boundary here is one of the interesting ones. It's a resonance of the way orbits precess with the precession of Neptune's orbit. Remember I said that the planets are mostly in a line, but not exactly, and so even those slight inclinations can trace histories of the solar system. The slight inclination of Neptune's orbit tells us it interacted with Jupiter when it was forming, and the way that tilt oscillates, the period of that oscillation, if you're in a short resonance, a 2-to-1 resonance with that, if your orbit oscillates on that, you also get cleared out. You get energy dumped into you. Not as fast as the mean motion resonance, which is why you see it's not like a really sharp boundary. But even these second-order and third-order dynamical events help sculpt our belt of asteroids. And so if you have this force here clearing out asteroids, it says that the stuff up here was born up there. Right? Objects like Pallas were born on these high inclination orbits and have stayed there since the beginning of the solar system. Now, this is just a plot of the orbits, but if we plot what we know about the physical properties, so here I'm showing albedo, so how much light is reflected off the surface, the fraction of incident light reflected, as color. And so, very roughly speaking, blue objects have the albedo of a hunk of coal. Purple is kind of new asphalt, old asphalt here, and concrete. So even the very reflective surfaces in the solar system are not super reflective. They're not white like these walls. They're kind of a dingy, reflect about 40-50% of their light. But already you can see, based on the colors of these objects, that these clusters are clusters not just of orbits, but of physical properties as well. And this helps inform our history that these objects are actually torn apart. So they're the end result of a catastrophic collision of between objects in the solar system today.
Just out of curiosity, what is this almost like a delta function there, or if I'm watching it right? It's almost a line. Yeah.
So this is so what I'm showing here are not the osculating elements. Osculating elements are, if you want to send a spacecraft, where is the object right now? Those vectors I showed you. Here I'm showing proper orbital elements, which I'll get into again on Thursday. I'll talk about the difference between the two. but effectively it's a time-averaged orbital element. So these are objects that are actually trapped, that's right at the center of that resonance. They're objects that currently, as far as we can tell, are trapped in resonance with Jupiter and are about to be evacuated. So there's a handful of objects in there that show up as being trapped. And it may be real, it may be an artifact of the way we calculate proper orbital elements. Again, I'll get into that on Thursday. But yes, that's an interesting set of objects there. So we clearly have a compositional gradient across the belt. Tomorrow I'll talk all about how we know, what we know, the various things we've learned about the physical properties. But this compositional gradient, we think, traces back to the frost line in the solar system. So as the sun was forming, you have a dust disk, you have gas throughout the disk, but at some point somewhere in the disk, the temperature went from hot to less hot, and at some transition point, ice went from a gas to a solid. We call that the snow line. So somewhere here, and we think it was around 3-4 AU, it really depends on your models of how opaque the disk is and how much self-heating you get, you transition to an ice-dominated regime. And I say ice-dominated, the amount of ice out here is expected to be a factor of 10 larger than the amount of dust. And by dust, I mean silicates, carbons, these kind of materials we see in a lot of our rocky meteorites. And so this ice line here, we think, has dictated the history of the solar system. It's why Jupiter was big, because it was right here, right at the edge. As that density was falling down, it was just outside that ice line, and so it had the most material to be built with. And it really tells a compelling story of you have a big Jupiter, a smaller Saturn, smaller Uranus, smaller Neptune. You have terrestrial planets in here because there was no ice. Everything works, and then we find extrasolar planetary systems that have nothing to do with any of this and look wildly different and totally throw our model into disarray. But right now, based on the evidence we have in our solar system, this looks like what happened for us. And I talked about it before, but the Oort cloud also helps us learn about this ice line. So the Oort cloud is a sphere of objects, again, about halfway, a third of the way to the nearest star. And these were objects that early on were kicked out almost to the edge of the solar system, put on orbits that were very nearly parabolic but not quite. And they got so far from the sun that the gravity of the rest of the galaxy became comparable to that of the sun, and they went from having parabolic orbits to entering into this kind of weird cloud shape. And what this means is they're very lightly bound to the sun, so a passing star, something nearby, can trigger them to fall in. What this would mean in terms of observations is that long period comets, those things with million-year periods, should be isotropic. And this is what we've seen with the long period comet studies. The short period comets come in on orbits that clearly have interactions with Jupiter. They come in from a population that is in a disk. We believe this to be the Kuiper belt. But the long period comets come in at a variety of inclinations that can only be sourced from a basically isotropic cloud around our sun. And so it's these objects that we think are the analogs for the interstellar objects. So it's objects from another star's cloud that maybe get bumped out that pass by our sun. And so what this tells us about the history of the migration in the solar system is that at some point, 4.5 billion years ago or so, right after the planets formed, you had the asteroids in here and you had Kuiper belt objects. And if you clear out the material in here, then what happens is if you take a single test particle, Neptune grabs it, sends it in, Uranus grabs it, sends it in, Saturn sends it in, Jupiter kicks it out of the solar system, and that will result in a net migration, where Neptune slowly walks its way away from the sun, and Jupiter ever so subtly comes in. And it's Jupiter kicking these things out of the solar system nearly to the edge that populate this Oort cloud. And so this motion, this evolution of the orbits of the giant planets, again, this is one test particle, but this implies there must have been trillions of multi-kilometer objects that Jupiter kicked out of the solar system. Again, arguing for a large population of free-floating comets just in interstellar space that we should fly by, these interstellar objects. So this is why we've been predicting interstellar objects for so long. Another line of evidence for this, right, just because I said, okay, well, Jupiter kicks stuff out, That's fine. Jupiter could also kick stuff in. On the bulk of it, you expect things to be kicked out more often than kicked in, because if it kicks in, it has another chance of passing by Jupiter and can get kicked out. If you get kicked out, you never see the solar system again. There could have been a spike in impacts. And so you would expect that as Jupiter is pushing stuff into the solar system, some of that stuff hits the Earth, some of it hits the Moon. And as the solar system runs out of material to move around, as we are left with only these stable populations, you'd expect a declining bombardment. And so what you would expect here is just as time progressed over from 4.5 billion years ago to 3.5 billion years ago, the number of impactors in the solar system would fall off at some flat rate as you consume the population. Some studies seem to indicate that this is not exactly what happened, that the fall off was somewhat regular, and then there was a spike 4 and change billion years ago. Now, recently this is being called into question, whether or not this spike actually exists, but there is some evidence that there might have been a spike, and this spike in lunar bombardment caused researchers to say, what could have caused this spike? What could have destabilized a population of objects in the solar system 4.1 billion years ago, when the solar system should be pretty quiet? Everything's kind of running out, you're running out of material, you don't have the catastrophic collisions between Earth and Mars like you did right in the 4.5 billion year ago mark. And the answer was the Nice model. So as Jupiter and Saturn are slowly stepping through this migration, if you set up the initial solar system right, then around 4.1 billion years ago, they crossed a resonance. They crossed a 2-to-1 resonance. And what this does is this amplifies their gravitational effect on all of the small bodies in the solar system. And so if you have a large population of objects in the Kuiper belt, then in this model here, 880 million years after the start of the simulation, they cross through this resonance. And what happens is these objects, the ice giants, change orbits rapidly. What happens is a lot of this population gets destabilized, and when you're when you're basically a billion years into the simulation, almost none of the Kuiper belt is left. This would imply that the Kuiper belt, even still a very large population, was 1 to 2 orders of magnitude larger when it initially formed. But it gives us some solutions. It helps say, why is Saturn's orbit not in a plane? Why is it slightly inclined and slightly eccentric? How did you get those objects trapped in that 1-to-1 resonance with Jupiter? Well, if you had this chaotic event in the solar system that was moving objects around because of this resonance, and then it broke, and then Jupiter and Saturn break out of that resonance, you can trap populations. You can have these residual objects left, either in 1-to-1 resonance with Jupiter as irregular satellites of the large planets, in resonance with Neptune. We have a similar problem where you have objects in 1-to-1 resonance with Neptune that can't get there in any normal gravitational way. And so there's a lot of support for this idea that this transition happened early on in the evolution of the solar system. What that means is that may be unique to our solar system. It's not necessarily true that this kind of configuration resulted in all extrasolar planets. And so perhaps this is what saved us from the fate of a hot Jupiter. Had we not had Saturn there, Jupiter might have migrated all the way in and cleared out the terrestrial planets. So this is one of the more major implications of the Nice model. Lately, another model has come up, the Grand Tack, where before the Nice model, the proto-Jupiter, the body that would later get the gas cloud to become Jupiter, migrated around and so actually pushed in almost to the orbit of Mars before being walked back out by the scattering process. It's a bit particular with what you assume the initial conditions are, but this model partly was made to attempt to explain why Mars is the size it is, but also that dichotomy you saw in the main belt of 2 different overlapping populations. This would help us understand that, okay, those dark objects actually formed beyond the ice line and were put in. And there is some support for objects that formed outside of Jupiter's orbit being entered into the main belt. And this is from the Dawn mission's observations of the dwarf planet Ceres. Ceres was observed to have ammoniated clays. which my geologist friends tell me, you can't do in the main belt today. Where it is, it's too hot. In order to get ammonia geologically to form a clay, you have to be significantly colder. The main belt today is too hot. And so it implies that wherever Ceres formed was much, much colder than where it is today. This could mean that Ceres is actually originally from the Kuiper Belt. That Ceres is, if you took Pluto and pulled it in to 2.5 AU from the sun, all that ice would melt, everything would volatilize away, and you'd be left with a husk that could be Ceres. And so, the Dawn mission has actually, answered some questions, but asked a whole lot more about how Ceres formed and where it is. And so, if you combine these, this is kind of the idea of what the solar system might have done early on. And so, we start with our giant planets as these lines, and Jupiter moves in, Saturn moves in, they move out, they hit, a bunch of masses removed. You have the Nice model occur right here, and so this is why all of a sudden they get broad, and so this is zero eccentricity effectively, and this is attempting to show the eccentricity of these objects as they move into the modern day. And so what started out with in our accretion disk of a nice gradient of compositions comes into our present day where you have a mix in the main belt, you have some Trojan objects trapped here, and you have a Kuiper belt that's also a bit mixed. And so this makes predictions for what we should see as we discover more Kuiper belt objects and characterize them more.
Just one thing that was unclear to me.
Yep.
What caused again the going away from the sun? What's the mechanism?
For Jupiter,
Yeah.
so the idea is that the bodies out here are scattering it. Again, it's a little bit contrived. There are some assumptions made that something is making it go away to fit the model. But it's not very well constrained right now. Yes, you're hitting the edge of where the models have gotten to, is that they force it to go away, and there are ways of doing it, but none of them are clean right now. So there is no good answer to that at the moment. But this is an attempt to explain why you have, the terrestrial planets is the way they are, the main belt is the way it is. Again, we're kind of backfitting. And again, if we look at this main belt, this is trying to answer this question, which is why does the main belt have such a variety of compositions? So I'll talk more about what these letters mean, but these are taxonomic types, so different assumed compositions. And so this was work by Francesca De Meo and Benoit Carey, trying to say, okay, what does the general composition look like as a function of distance? We see in the inner part of the belt here, it's dominated by silicate-rich objects. In the outer part here, it's dominated by these opaque-rich, these carbon-rich surfaces, but there is still some of this silicate-rich material. But there does seem to be a general trend here. There seems to be two overlapping populations. We see a distinct population out past the 2-to-1 Jupiter resonance and the Cybele, which is traced to the Hildas and the Trojans as well. And so it does appear to show a step in composition as a function of distance. And so is that indicative of how the main belt formed, or is that indicative of populations that formed in separate locations being mixed? Because those two things have very radically different implications for how you make an asteroid and how finely you have to tune your protosolar disk. So in the last few minutes, I just want to close with some close-up images we've gotten of some of these minor planets from the various spacecraft that have gone there. And so these are the Dawn image missions. This is from Ceres. This is Vesta. This isn't the full disk of Vesta, just because I really like this image. This is showing, so Vesta itself is kind of a, it was a sphere, and it underwent a catastrophic collision that left a giant hole. So the sphere should continue here. A huge amount of material is ripped out. This is the central peak of a crater that is almost the size of the body itself. These lines here are crumpling from that impact that shattered the body and left these, global scale creases from that impact. Ceres here, again, if this is implanted from an outer region of the solar system, it seems pretty smooth. It doesn't show the same cratering, which you might expect if there's volatiles just under the surface. If there's an ice rock mix just under the surface that mutes the formation of craters. We also see Akatur crater here, which these, when we got real close and took very good images, are salt. They're a deposit of salt, and they're young. What the interpretation is that, and they're right at the center of this crater too, something hit that crater, warmed up a salty brine that had frozen just underneath, and that brine is slowly leaking out. The water volatilizes away, and you're left with salt deposits. Again, speaking to a formation that was very water-rich, possibly well beyond the orbit of where Jupiter is today. When we look at our smaller objects, so this is Bennu and Ryugu. So these are the two targets of OSIRIS-REx and Hayabusa 2. And they look kind of strangely different from anything we had expected. They are piles of gravel. There are no smooth surfaces here. If you go down, if you get closer images of these, they're just piles of boulders kind of in the soccer ball size and football size. They have things just sitting on the surface. They are accumulations of something that, again, these family-forming events, catastrophic impacts that shatter material and it loosely bonds together. And this shape here, this diamond shape, implies that as they're spinning, right, these are small objects with very little gravity. The centrifugal force as they spin causes stuff to roll to the equator. And if you spin it fast enough, and again on Thursday, or I think tomorrow I'll talk about Europe, maybe Thursday, objects can change their spin from sunlight. As you spin these up, the gravitational potential on the surface can reach zero, and material can lift off and form moons and actually kick material off. And we're seeing now, for the first time, objects in the process of self-destructing. We assume from landslides as these things are right at the critical spin barrier. When we get to smaller objects, we see these weird contact binaries, things with somewhat clear head and body. This is Itakawa from the first Hayabusa mission, and the Chinese mission Chang'e 2 went to, which one's this? Totatis. Again, weird bowling pin shapes with, in some cases, this is very smooth. It's a pond of dust that's settled in the gravitational low here, but still boulders on the surface that are a fairly large fraction of the size of the main body. And we see a variety of structure in the comets as well. So we have Wild 2, Hartley 2, and 67P Churyumov-Gerasimenko, showing a variety of activity. You see smooth regions here, again, this bilobate shape with a smooth neck. We see, again, a weird bilobe shape for 67P with jets shooting off, incredibly strange cliffs that implies some serious changes in evolution over the last 4 billion years from when it formed. And then we saw, Wild 2 looks kind of boring, which immediately makes you say, what if those dark asteroids are collections of this material? This bright heart-shaped feature is nitrogen ice, and the close-up images from the flyby showed convective cells within the ice. Very slow convection, but there's geology going on in the outer edge of the solar system where there should be no heat, where the sun is just a bright star, and there's geology happening. You see Karen here, again, with that same dark material, but a major crack across the surface. And it's assumed Pluto has also 4 other tiny moons, that this system underwent, again, a catastrophic impact that ripped it apart, potentially forming Karen, and almost certainly forming the other 4 moons in the system. MU69 has had a quieter life. And so again, bilobate with a weird bright region at the neck, and what are interpreted as craters. Unfortunately, this is the best image we have and the only image we have other than one from the complete backside. So we don't have a really good 3D geometry of this yet. But you can already see a strange formation system here where it looks almost like a bunch of balls of clay stuck together. So my next topics for my next 3 lectures, tomorrow I'll be talking about composition and physical properties, how we know all of these things I've said we know about composition, about this is silicate rich, that's carbon rich. Thursday I'll be talking about orbital and collisional evolution, these families, things that have crashed into each other, made thousands of fragments that have evolved over time, and how we can undo that, basically back up that movie to see how they formed. And then on Friday I'll be giving some mission highlights from the NEOWISE mission and talking about our next plan for NEOCAM. So if you have any other questions, please feel free to ask. Otherwise, thank you for your attention.
Yeah, thank you for the lecture. Well, I just have maybe a naive question about the taxonomy.
Yeah.
That taxonomy is based on photometric observations or spectroscopic?
Both. And I'll talk about the two different kinds of or the many different kinds of taxonomy we've gone on. We've done with both of those. There are more photometric surveys than spectroscopic because it's easier to get photometry. But it's more, you get more information with spectra. And so, yeah, we have both kinds of dynamics happening. And one informs the other.
One question that was bothering me is that you mentioned that you have to have this aluminum 26 radioactive coming from some supernova that can probably date most of the time. So
Yes.
my question is there any other evidence, for example, other radioactive material, other depositions that indicate confirm this?
Yeah, no, there's a lot of radioactive material history. It's just that aluminum 26, the supernova form a lot of it because it's an alpha element, and it releases a lot of heat quickly. So it dominates the differentiation process in terms of radioactive heating. We still have radioactive heating in the Earth today from uranium decaying, etc. But that was what dominates, because of its quantity and its short half-life, it dominates the evolution in the early days. But it is convenient. I mean, it's an oddly convenient timing that the supernova went off when the solar disk could have accepted the material and incorporated it. It wasn't too late and it wasn't too early. It happened at a very convenient time for us. And so now there's a question of what would have happened, because it's not from whatever triggered the collapse of the protosolar disk, because that collapse actually takes tens of thousands of years, and so that would have burned out already. So there was a secondary supernova that implanted our solar system at just the right time to be useful to make Earth, which is kind of uncomfortably anthropocentric.
In one of your slides, you mentioned the year 18,000.
1800, yeah.
Then, can I tell you one short story related
Please.
the name of this building
Yeah.
to the solar system
Yeah.
in that century?
Yeah.
It's the name of this building is dedicated to Emmanuel Lier.
Okay.
Emmanuel Lier was a director here, and he worked with Leverrier. But Leverrier, when he discovered Neptune, he became so nasty guy, and they used one special things for him, and then he escaped Leverrier and he came here.
Yeah.
But after, as a director, then Leverrier was looking for a planet called Vulcano.
Yep.
You know this story.
Yeah, Vulcan.
But once Emmanuel Lier was observing here, and suddenly they saw a body. It was not Venus crossing the sun.
Mm.
And he says, "Oh God, I cannot believe that this body is Vulcano." He was not Vulcano. He didn't publish. He was.
Oh.
Actually, the people believe that it was the first Neo observer.
Yeah.
Historically, point of view.
Yeah.
But it's a funny story because he said, "No, it's not Vulcano."
Yeah, no, people have been looking for the planet inside Mercury forever, and we haven't found it yet. We don't think there should be one dynamically. We understand the dynamics of the inner solar system well enough now. A lot of the problems with Mercury's orbit that would have been solved by Vulcan were solved by general relativity. And so the precession of the perihelion of Mercury was one of the key aspects that general relativity fixed. And so got rid of the need for Vulcan at the same time.
Yeah.